Okay, chemistry critters, we're going to work out some examples on determining empirical and molecular formulas. So let's get started with refreshing on the definitions of those. So empirical formula, keyword, simplest whole number ratio. And it's your only option for anything crystalline. For example, in the ionic compounds, you've got this alternating crystal of the ions with opposite charges, and that can be extended to infinity in any direction, so you don't really have one set formula, so you're stuck just writing the simplest whole number ratio. On the other hand, if you've got something that's a covalent molecule and it has a beginning and an ending, water, then you can just write a molecular formula, which is the actual number of atoms in the molecule. It might be equal to the empirical formula. It might not, as we'll look at some examples later. So, move. So recall that percent composition is the mass of each element divided out by the molar mass. So for instance, water here, the molar mass, 2 H's, 1 O, is 18.015. And so if I have 2 hydrogens, so that's the mass of my hydrogen in there, divided by the whole mass times 100%. I get 11.2. And if we do the same thing with oxygen, the 1 oxygen in there divided by the whole mass gets us 88.8%. What we're going to be doing now is working this backwards, starting from the percentages and working towards a formula, either empirical or molecular. Strategy, like most things, we're going to be working in moles. So whatever your mass unit is, we need to first convert that to moles. If your data is given in percent, we're just going to pretend it's grams. So whatever it is, pretend it's grams. If it's percent, let's just assume that you have 100 grams of the substance, so the percent becomes your mass. Then, here's a math term for you. We're going to normalize, and that means divide out by the smallest number of moles. So if you've got elements A, B, and C, whichever one of those has the smallest number of moles is what you're going to divide the others by. At that point, you're going to hope after normalization that your values are really close to whole numbers. If not, we're going to need to look for what those fractions would be. If it's a decimal, what fraction it is, so that we can multiply out by the common denominator. So that's going to be our strategy. Convert mass units to moles, divide out by the smallest number of moles, hope that we've got whole numbers. If not, convert to fractions. Okay, so first example here, I was given percentages of the 3 elements in a compound: potassium, chlorine, and oxygen. And so I want to be like, right, these are grams. 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 So I'm just pretending everything is in grams. And so my first step, as I mentioned, is we're going to find the moles of everything. So I'm going to start with my potassium, 31.90 divided by molar mass, which is 39.083, and that gets me, looking at my crib sheet here, 0.8162. It's a good idea to keep all of your sig figs in this problem, because we're going to be converting things to fractions. So the worrisome thing might be if your fraction needs to be like 1/4 versus 1/5. If you're kind of sloppy with your rounding here, you might not tell which way you need to go with that. So try and keep your sig figs as many as you can. It gave me data here with 4 sig figs, so I'm going to run with 4 sig figs through the problem. Okay, chlorine, 28.93 divided by molar mass. Again, keeping my 4 sig figs. And oxygen, 3917 divided by 15.999 gets me. At this point, I could write the formula of this substance with these ratios, and it would be an accurate formula for whatever this is. So that would be the formula of our guy. But that's not how we like to see our formulas. We like to see them expressed in whole number ratios. So let me strike this, and we'll do that normalization step. Okay, so now we're going to normalize. This guy's my smallest number of moles, so I'm going to divide out by that. 6, 0. Not that that matters too much for this one, because it's going to still be really, really close to 1. So this comes out with, as far as my sig figs are concerned, as essentially 1. This one, of course, is exactly 1. And this comes out, as far as sig figs goes, 3. So, like I said, we were hoping for whole numbers. We've got to within our rounding error, we have whole numbers. So my formula on this is going to be KClO3. So we've got potassium chlorate. And that is my final answer right there. Okay, so on this slide, what we've got is a compound that contains 3 elements, calcium, nitrogen, and oxygen. And it tells us that we have a 5-gram sample that contains so many grams of calcium and so many grams of nitrogen. This is a really common thing to see on these problems, is to leave out one of the elements, in this case oxygen, but you always have enough information to get it by subtraction. So if 5 grams contains this much calcium and this much nitrogen, then the difference is going to be the amount that's oxygen. So let's figure that out first. That way we have all of our data. So 5 grams minus 1.52 minus 1.06 gets me 2.42 grams oxygen. Okay, now we've got all of our stuff, and let's go through the normal process. I'm going to find my moles. So 1.52 divided by 40.078 gets me 0.0379. Like I said, I'm going to be careful with my sig figs here. Got 3 sig figs there, so I'm going to keep 3 sig figs. I'm going to run with that on all my data. Okay, nitrogen 1.06 divided by 14.007 gets me 0.0757, and oxygen 2.42 divided by 15.999 gets me 0.0, oops, not 0.0, 0.151. Okay, normalize. This guy's my smallest, so I'm going to be dividing everything out by 0.0379. Okay. Naturally, this guy is 1. This is 1.09. 9 to 3 sig figs. And this guy is 3.98 to 3 sig figs. So again, hoping for whole numbers, and I'm comfortable calling this 2 and calling this 4. So I'm ready to write a empirical formula for this. Sorry, my pen is not wanting to work. Okay, so I have calcium, 2 nitrogens, 4 oxygens. That would be my empirical formula. This would be an adequate answer. If you're good with your polyatomic ions, you would probably recognize this as calcium nitrite, because the nitrite is NO2, and we've got this. And that makes sense as far as charges go, because calcium is a +2 ion, nitrate is a 1- ion, and we would need 2 of them. So this would be entirely adequate for an empirical formula. Bully for you if you can recognize that it's calcium nitrite. Okay, we're going to get a little trickier with this one. We've got a compound containing sodium, chromium, and oxygen. 2.5 gram sample has this much sodium and this much chromium. Again, they're leaving off that extra bit of information, but that's no big deal. We'll get it first by subtraction. So 2.500 minus 0.439 minus 0.993 gets me 1.068 grams of oxygen. Now I have all my data, and we can go ahead and do the normal process. So I'm going to find my moles. So 0.439 divided by molar mass of sodium, 22.990. That gets me 0.0191. Keeping 3 sig figs. 0.993 divided by 51.996 is the mass of chromium. 0.0191 again, and 1.068 divided by 15.999 gets me 0.0668. Normalize, these guys are the same and they're my lowest ones, so I'm going to divide out by my lowest one. So 1, 1, and 3.49. Not okay to round this to the wholes, to the next wholest number. For these kind of problems, it's going to work out. If you need to round it to a whole number, it's going to be pretty much right on that whole number. So this cannot be rounded to 3, cannot be rounded to 4. What you need to recognize, though, is that this is 7/2. So spotting 0.49 as decimal equivalent of a half. So this is 7/2. So I'm going to put everything now with a denominator of 2. So 2 over 2, 2 over 2. And so what we can do now to get our empirical formula is to take all of our fractions and multiply them by 2 so that we can cancel out our common denominator of 2. And so that leaves us with an empirical formula of 2, 2, and 7. So let's write that out as final answer. Na2Cr2O7. And again, if you're good with your polyatomic ions, you would recognize that this beast right here is dichromate, and it has a -2 charge. And so it makes sense then that you would need 2 of the sodiums to cancel it out. So there we go. A little trickier with that. This is something that you'll need to be aware of. So be on the lookout for decimal equivalents of a half, a third, or 2/3, a fourth, 3/4. I think probably the worst thing that you might see would be a fifth. So you could have 1/5, 2/5, 3/5, etc. So be on the lookout for these fractions and try and associate them with some fraction so that you can multiply out by the common denominator. We'll look at one more where we have to do this. Okay, very last one here. Now we're asking for a molecular formula. And if you'll notice, we're given one other piece of information that allows us to do that. If you're asked to solve for a molecular formula, you'll also be given the molar mass of the whole compound. So this will come into play later. The first part, though, is finding empirical formula just like normal. And then we can use this with the empirical formula to get our molecular. Okay, so I'm going to find my moles, just as before. 48.38 carbon divided by molar mass of carbon. 4.028. So I've got the luxury of 4 sig figs, at least for the carbon and oxygen numbers, not for the hydrogen. 8.12 divided by 1.008 gives me 8.06. And 53.50 divided by 15.999 gets me 3.344. So there are my moles. Time to normalize. This guy's my smallest. Naturally 1, 2.410, 1.205. So again, here we've got a problem where we're not comfortable rounding this, either of these, to the nearest whole number. I need to say, okay, I recognize 0.2 as a fifth and 0.4 as 2/5. So I'm going to be thinking of these as this is 6/5, 12/5, and 5/5. This kind of illustrates why you really need to be careful with your sig figs on this, because if you're a little loosey-goosey with your rounding, you might confuse this guy for a fourth and this for like 2/4 or a half, and then your empirical formula is going to be something entirely different, because we need to multiply out by 5 and cancel those out so we get an empirical formula of 6, 12, and 5. Okay, so let's scoot this up. Well, not that far. I need that molar mass. There we go. Okay, so I have C6H12O5. And this is my empirical. Could be my molecular, don't know yet. What I do know is the molar mass of the entire compound. So I'm going to figure out the mass of my empirical and see, is it the same as this, or is it smaller than this? And if it's smaller, how many times smaller? I suspect that it's probably going to be smaller than that. So let's tabulate this. So I'm going to do 6 of those times molar mass, plus 12 of those times molar mass, plus 5 of those times molar mass. So I'm just going to compute molar mass just like normal, and all of that for my empirical formula sums up to 164.16 grams per mole. Yeah, that was considerably smaller than this. So our last step now, zoom out, trying to get more writing space but not lose my, my molar mass number. So I'm going to take my molar mass of the entire compound and I'm going to divide it by the mass of the empirical compound, and I'm going to look for a nice whole number ratio, and in this case, to our number of sig figs, this is 3. So what this means is the actual compound is 3 times bigger than our empirical. So if our empirical is C6H12O5, then the molecular formula is going to be C18H36O15. And so this is going to be molecular. So if your problem asks for molecular formula, you just have one more step to do after you've done your empirical formula. So compute your, wrong thing. Compute your empirical formula just like normal. Calculate its mass. See how many times larger, could be the same, but how many times larger the molar mass of the whole compound is. Should be reasonably close to a whole number, and then you can just distribute this to your empirical formula to get that. So that's it for empirical and molecular formulas. Hope you guys have lots of success on the practice problems, and we'll talk to you later.